No, these are the course. For the other class? I don't know. It was more abstract than the other one. Did I sign up for this one? No, no. It's not too much. It's not really hard. Good morning, everyone. So in the previous lecture, we introduced linear algebra, and we touched on what a numerical method is. Numerical method gives me an approximate solution to a certain problem, whatever that problem is. And that numerical solution is probably usually is very close to the actual solution, or to the exact solution. The numerical solution that you end up with could either be exact. For example, when we said solve x squared equal 2, the numerical solution was never exact, because the numerical solution always had 1.4. So whenever you squared x, you never exactly got 2. But if I tell you solve x squared equal 9 with a numerical algorithm, at some point you'll find that x is equal to 3. Whatever numerical algorithm you use, you will find that numerical algorithm should give you that x is equal to 3. Or it could give you, if you're not really careful on the accuracy, it might give you 2.99 and so on. But if you're careful, if you're careful with the accuracy, you will obtain x equal 3 using any numerical method, because 3 is within the means of that numerical method. So in this lecture, we're still covering the introduction. So we're going to talk in this lecture about stress, strain, and about the relationship between the stress and the strain. And then we're going to introduce the actual equation that the finite element analysis method is trying to solve. So the solution of any finite element analysis is the stress at a point, the strain at a point, or the stress at every point in your object, the strain at every point in your object, and that is done through solving a certain differential equation. So by the end of today, we should know what the stress is, what the strain is, and what is the equation that we're actually trying to solve. So we're going to start by what is stress. And the famous example that I always use is, let's put here P is equal to 1, whatever units are, whatever units you use, and let's say the area is equal to 1 unit, and this is a square cross-sectional area. And let's ask the question, what is the stress right at this point? Can I write this? Is this what you see? What do you think? That's fine.
Yeah.
Does everybody agree?
Depends on the unit.
Depends on what unit. Okay.
What P and A.
So, 1 unit of force over area. Okay, what else? Any other? Okay, what about the stress here? Is it the same? Is it also 1, or is it different? Also 1? Okay. So, and is it different here? Or is it the same? That's it. Now, whoever is saying 1, you're all assuming that E is constant everywhere. And let's say that's fine. It's an elastic material and E is constant, so that's fine. So let's ask another question. Is there shear stress? Okay, let's see. So there should be 30 students in front of me. So I want the total number to be 30. Who says yes? So is there shear stress? Who says yes? Okay, 0. Who says no? There isn't 30. That's not that. Who says no? 1, 5. So 5?
It depends on which type we are saying.
Exactly. So I cannot, so all these numbers is actually, I can't say the stress here is 1. If I'm looking at a point, I don't say that the stress at a point is equal to a value. And I can't, there's shear stress, whether there's shear stress or not, depends on the plane that I'm looking at. So the stress, in fact, and there's a proof in your notes or in your book, stress at a point is not described by one value. It's described by 6 values, and these 6 values are actually related to the coordinate system chosen. So in fact, when you said 1, what you were saying is that if I choose this to be E1, and this is E2, and this is E3, then at this point, under this P equal 1 unit, and A is equal to 1 unit. So under the state of stress, the stress at point A, that's called sigma at point A, is made out of 1, and everything else is 0. The stress at a point is not given by one value. It's given by 6 values, and because this is a 3 by 3 matrix that is symmetric, so it's given by 6 values. Now, when I ask what's the shear stress or what's the normal stress, it depends on what plane, because the function of the stress, we know that a matrix, the function of a matrix is it takes a vector and gives me another vector. That's the function of the matrix that we studied last time. A matrix. So, let's just draw it. I have R3 and R3. The matrix takes one value from R3 and gives me another value of R3. And the function of the stress matrix is exactly the same. It takes one vector and gives me another vector. Now what is this vector? It takes the vector that describes the plane that I'm interested in and gives me the force on that plane. Or force vector on that plane. So for example, if I consider this plane with a unit that's equal to 1, 0, 0, what happens when I multiply sigma E by n? You will get 1, 0, 0, which is equal to force per unit area vector, force vector per unit area on this plane. So basically on this plane, with this coordinate system, the force per unit area is equal to 1, 0, 0. The shear, well, find the component of this, and we'll talk about it in a bit, on this, in this direction, and you'll find that the shear on this plane is 0. But this is not, okay, well let's consider this plane. I'm going to call it NB is equal to 0, 1, 0. Well, the stress, let's call this stress. The stress multiplied by n b, which is equal to 1, 0, 0, 0, 0, 0, 0, 0, 0, multiplied by 0, 1, 0, is equal to zeros. So the stress on this plane, so this plane does not feel any stress under this load. Now you take any inclined plane and you'll get a certain. So on the inclined plane, let's put cosine theta, sine theta, and 0. What do I get? This multiplied by this again, cosine theta. Which tells me that on this plane, I have a force in the force vector in this direction, and the force per unit area vector is equal to cosine theta 0, 0. Is there shear stress on this plane? Yes, because if you take the component of the force in this direction, or this vector in this direction, you will find the value. Is there normal stress? Yes, because it has a component on this in this direction. And indeed, if you have a if you actually construct the beam that way, and for some reason it comes into two pieces, if those pieces are like this, you need to put any sort of shear, something to take your shear. So it really depends, the force per unit area depends on the plane. And the stress at any point, the stress, the function of the stress, or the stress matrix, or the stress tensor, takes a vector in R3, usually a unit vector, and gives me a force vector in R3. This force vector, which we call the traction vector, is equal to the transpose of sigma multiplied by n. Since the stress is symmetric, I'm just using a certain convention. That's why I'm using sigma transpose. But it's symmetric, and sigma is equal to sigma transpose. And in my notes, or in, if this is the direction E1, this is sigma 1, 1. This is sigma on the plane 1 in the direction 2. In other books, you might find that this is sigma 2, 1. So depending on which book you're reading, you might find this to be sigma 2, 1. Okay? But here, or in my convention is, I mean, it's not my convention, but the convention that I'm following is that the first number relates to the plane, the second number relates to the direction. Okay, so the stress matrix, and here's the convention for the stress, sigma on 1, sigma on 3, sigma on 2. So this is, at any point, you can imagine that this cube is very small. The stress matrix, according to this coordinate system, is defined by those numbers. Now those numbers will change if you adopt a different coordinate system. Not only this, the stress matrix is symmetric. Why is it symmetric? Because if you look at this cube from the side, sigma on 1, sigma on 2, sigma 2, 1. And you take the sum of moment here is equal to 0. You'll find that sigma 2, 1 will be equal to sigma 1, 2. And so the stress matrix is symmetric because the material does not have any what we call internal moments. If you have a material that aligns itself or can carry what we call internal moments, but these materials might exist, I don't know, but I've never seen any material like this, or I've never heard of a material like this. In general, most materials, or materials that we deal with, do not have internal, I don't know how to call it internal moments, but they have a symmetric stress. If you, just to explain what I mean, do you guys know anything about MRI? MRI machines? Do you know what it does? So when you put when you put a certain magnetic field, the water molecules start aligning themselves or start applying certain moments inside the material on a very localized level. So this might be something that, if you calculate the stress matrix in this for such a material, then you wouldn't have a symmetric stress matrix because you have other forces acting on your material. But in general, all the materials that we deal with do not have anything here. And so when you calculate the moment around this point, you get that sigma 2 is equal to sigma 2. Now we're talking about a very localized level. This is very small, and this is very small. So we said that the stress matrix is defined or the stress is defined by a matrix, and this matrix gives me, usually I'm interested in the design. I'm worried about a plane failing, or if I'm worried about a plane failing, I would like to know what's the normal stress, which I'm going to call sigma n, and what's the shear stress, which on the plane with a normal n. To find this, it's just a matter of, so I have a plane with a normal n, and I'd like to find the stress that's perpendicular in that plane, and the stress that's parallel to that plane, and that's just a matter of a little bit of linear algebra. If this is n, and this is the force per unit area vector on that plane, and sigma n is equal to Tn dot n, which is a real number. And that's called the remaining vector tau n. The shear stress is the norm of this remaining vector. Now this remaining vector is equal to Tn minus this vector. Now this vector has a magnitude of sigma n in the direction of n, and that gives you the shear. So the magnitude or the norm of this vector gives you the shear stress on the plane. Now this stress matrix was derived, or the stress at a point was shown to be a matrix in the 1700s by, I think, a mathematician and scientist called Cauchy, and that's why this is called the Cauchy stress tensor. So the principal stresses of the Cauchy stress tensor. So we in a certain coordinate system, the stress matrix has certain components, and it's symmetric, and we now understand what these components mean. So this is the physics, and this is the math. Now the math tells me that if I have a symmetric matrix, then there is a coordinate system in which this matrix is diagonal. And this is aligned with its eigenvalues. So this is a certain coordinate system. There's another coordinate system, E1 for E-1, E-2, E-3. And in this coordinate system, sigma prime is equal to 3 values. And where this is equal to sigma prime 1, or I call it sigma 1. This is sigma 3, and this is equal to sigma 2, which are the principal stresses. So when you're using finite element analysis, you're going to find output the maximum principal stress. What's the maximum principal stress? It's calculate these eigenvalues at every point and find the maximum number of these 3 numbers. That's the maximum principal stress. Finite element analysis software also gives you the minimum principal stress. What's the minimum principal stress? Calculate those 3 values and find the actual minimum of these. The mid principal stress, well, calculate the third. So whenever you output any maximum principal, minimum principal, you're outputting the eigenvalues of the stress matrix. Not only this, the software will give you can vector plot the directions of the maximum principal stress. So you end up with a beam, and for example, and then you end up with vectors like this. These vectors are basically, I calculate the stress matrix at this point. At this point, I'm giving you, there are 3 values for the stress, for the principal stresses, and 3 eigenvalues. So three eigenvalues and the 3 eigenvectors. This direction corresponds to the direction of the maximum principal stress, the eigenvector associated with the maximum principal stress. You'll always find that the other ones are perpendicular. And why are they perpendicular? Because the math tells me that the eigenvectors of any symmetric matrix can be chosen to be perpendicular to each other. Because of that, you'll find that the maximum principal stress and the minimum principal stress and the mid-principal stress, they're all perpendicular to the directions of the eigenvectors are all perpendicular to each other. And at this point, for example, or let's pick this point, if I extract the cube of the material, I'll find this is sigma 1, sigma 2, and sigma 3. Now this is the physics, and there's no shear stress on any of those plates. There are other outputs that the finite dimensional analysis software will give you. One of those outputs is the hydrostatic stress. Now what is the hydrostatic stress? The hydrostatic stress is the average of 3 values, which are the diagonal values of the stress matrix. And if you're working in soils, this is really an important part in the design of soils. And depending on the software, you might get something called the first invariant of the stress matrix. The first invariant of the stress matrix may be the trace. You have to read what the software means by the first invariant, because if you remember what we said, the matrix that's 3 by 3 has 3 invariants. These invariants do not change if you choose a different coordinate system. So if you're dealing with the stress matrix, the first invariant is the sum of the diagonal, but the hydrostatic stress is the first invariant divided by 3. So it depends on which software you're using. It might tell you, it might output the hydrostatic stress, or it might be outputting the first invariant. Another important measure of stress that any finite element analysis software outputs is the deviatoric stress tensor. So the deviatoric stress tensor is calculated as follows. Basically, we assume that our stress matrix that's calculated is equal to the deviatoric stress tensor plus this average value. And so from here, this deviatoric stress tensor will be equal to sigma minus pi, where p, of course, is a real number, and I is the matrix. Now, why would I do this? Why do I care for such a decomposition? Why would I decompose the stress into a deviatoric stress and what we call a hydrostatic stress? So this is called deviatoric and hydrostatic. Because in linear, elastic, small deformation materials, linear, elastic, small deformation S is responsible, or let's say is the stress component responsible for shape change, while P is responsible for volume change. And depending on your material, you might be more interested. So in general, steels were very when you design a steel material, you're more worried about S than P. Usually materials or steel material is weaker when you try to change its shape. By changing shape, I mean the following: that this deformation can be assumed to be the sum of two deformations. An expansion plus some sort of a shear deformation. And this is the one that S is responsible for, and this is the one that P is responsible for. And the famous stress measure that everybody who uses finite element analysis outputs is called the von Mises stress. And if you were going to use the finite element analysis to design anything, the one thing that you're going to output, the first thing that you're going to look at, and the first thing that every paper that I've seen in biomechanics or in any material, maybe concrete is different, I don't know, but any paper that I've ever seen, the first thing that I see here's the plot of the von Mises stress on your on the object. And you look at the maximum von Mises stress and say this is the area of concern. Now, the von Mises stress is nothing but the second invariant of the deviatoric stress tensor. So it's an invariant. It does not really depend on the coordinate system, which is good. And it has the following. Really, depending on which stress matrix you use or which coordinate system you use, it has different formulas, but they're all equivalent. If you just calculate it from sigma, and so on, this is the equation. If you calculate it from sigma prime, which is equal to sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, sigma 3, you get this equation, which comes from this equation, which comes from this equation, but they're all equivalent. And you might have seen square root of 3 over 2 Sij, Sij. They're all equivalent, where S is your deviatoric stress tensor. Okay, so this is what the stress is, and these are the numbers that any software will output once you calculate the stress. Once you calculate the stress in your object, the software will give you any of those numbers. Now, the objective of finite element analysis is to solve this problem. I have an object that's sitting in an undeformed state, and I have certain boundary conditions on it. For example, I have that this is constrained from moving. I have a force here. I have a displacement here. And the objective of the finite element analysis is to find a deformed shape. And in this deformed shape, it needs to find the new location of the material points. If this was the location of the point, now where did this point go? And this f, which is a mapping function, is just a map that tells me, oh, your point was here, now it's here. F is smooth and differential. Now this is important to, there's a big limitation or not limitation. You need to understand what I'm saying here. I'm saying F, which I need to find, which is the objective of which is the objective of any finite element analysis run. This F, this function, is smooth and differential, which means it takes a line and gives me a smooth curve. However, in the finite element analysis, because it's a numerical method, the solution that I get is not smooth like this. If you've seen any finite element analysis run, there's a lot of elements, and each element has just a straight line. So even though you get, so for example, if you have an originating line, and this is the actual solution, the finite element analysis actually gives you this solution. Which takes us back to the difference between, I'm just going to scroll all the way up, which tells us the difference between this and x is equal to root 2. Because the elements, my approximation is always made out of straight lines, and because the actual solution is not a straight line, I will never get that actual solution. So my assumptions, or my numerical method, it is getting closer to the actual solution, but it's not really the actual solution, because the deformation shape that I'm assuming is made out of small straight lines, but the actual solution that I'm looking for is smooth. And so in the finite, in general, at every point, so now I'm looking for this f, or this function that tells me where x went, and the displacement at this point is given by the new position minus the old position. The new position is equal to f of x minus x. And this, in general, is equal to u1, u2, and u3, which are functions of the position. Because the displacement here, the displacement vector, might be in this direction, while the displacement vector here might be in this direction. So this point moved downwards, and this point moved upwards, and they both moved horizontal. Now, in order to differentiate between an object that basically just translation and an object that actually deforms, the difference between this and this is that no gradient or zero gradient, zero gradient for u, non-zero gradient for u. So basically what I'm trying to say is that when do you see strain? You see strain when points in your material start moving with respect to each other. If all the object just translates or rotates, that means all the points maintain the same distance with each other. But if points start moving with respect to each other, if that point moves 1 centimeter, but the one next to it moves only 0.5 centimeter, that means that there is a gradient in the displacement. The displacement is not the same, and that means that there is now a strain between those 2 points. And hence, we calculate the strain, and we use this strain matrix to describe our strain usually. And this is the one that we're going to use in our finite element analysis course. That describes the state of strain at every point. And this is calculated using this formula. Half the gradient of u plus the gradient of u transpose. What is the gradient of u? If u is equal to u1, which is a function of x1, and u2 function of x2, and u3 function of x3, the gradient of u is a matrix made out of the following numbers. Partial u1 by partial x1, partial u1 by partial x2, and because we're interested only in translation, in deformation and not rotation, and for those who are taking solid mechanics, we're going to spend more time on this. We take the symmetric part of this matrix, and that's why we calculate epsilon as half the gradient of u plus the gradient of u transpose. We take the symmetric part. And we calculate this matrix, and this matrix gives me a measure of how much strain there is at a point. Now this matrix is tied to a coordinate system. And every value has a meaning. Every entry has a meaning. So this has a meaning, it has some physical meaning. So what are the physical meanings of these? First one is partial u1 by partial x1, or partial u2 by partial x2, or partial u3 by partial x3. What do these values mean? It means the following. If I have a very small element where this point moved u1, because I'm assuming that everything is smooth, this is u1, and this is the location of the material x1. I'm assuming that the horizontal displacement is a smooth function, which means at any point, if this is u1, its neighboring point at a distance dx1, because of the smoothness of my function, this point, the displacement is equal to u1 plus a little bit more. This little bit more is related to how E1 changes with x1 multiplied by dx1, plus even other terms that are a function of dx1 squared and so on. Which means if this point has moved horizontal displacement U1, this point has moved a horizontal displacement that's equal to this. Plus even a little bit more. If I want to calculate the strain in this direction, strain in direction of E1, I'm going to call it, let's say, longitudinal strain in the direction of E1. Let's call it epsilon 1. This is equal to delta over L. But delta is equal to the difference between the displacements. And the difference between the displacements, the difference between the horizontal displacement on the left and the horizontal displacement on the right is partial U1 by partial x1 dx1 divided by the length. This will cancel this, so you end up with partial U1 by partial x1. And so epsilon 1 gives me the engineering strain, which we know as delta over L, in the direction of the unit vector E1. And so epsilon 2 gives me delta over L in the direction 2 Epsilon 3 gives me delta over L in the direction E3. Epsilon 1, 2 is given by this. Now let's try to understand the physical meaning of this term. So if I have this small piece extracted from the material, after deformation, if there's shear strain, it will look like this. Where if this is the horizontal displacement U1, then at this point, I have U1 plus how much U1 changed with respect to x2 multiplied by delta x2 plus even a little bit more. And if this is the vertical displacement U2, then this is the vertical displacement U2 plus how much U2 changed with respect to x1 multiplied by dx1. Now the shear strain that we are used to, or the engineering shear strain, is equal to the sum of the angle theta 1 plus theta 2. Let's call this gamma 1, 2. This is equal to theta 1 plus theta 2 because of the small angle and small deformation. The tan of the angle is equal to the sine of the angle. So basically, this theta 1 is nothing but this distance divided by this distance. So I can approximate theta 1 with partial U1 by partial x2, and I can approximate theta 2 with this distance divided by this distance. So delta x1 will cancel delta x1, and I'm going to be left with partial U2 by partial x1, which is equal to 2 epsilon 1, 2. And so the diagonal, the off-diagonal entries in my small strain matrix gives me the engineering shear strain in the corresponding planes. And again, this is tied to a certain coordinate system. And since epsilon is symmetric, there is a coordinate system in which is diagonal. And the software outputs the maximum principal strain, the minimum principal strain, or the mid-principal strain, and their directions as well. And in a linear elastic material, you should find that the directions of the principal strains align with the directions of the principal stresses. But that's only for linear elastic materials. Linear elastic isotropic materials. Which basically what I'm saying, what I'm saying is the coordinate system in which the stress is diagonal. Here's an example. Just don't want to confuse you without an example. Imagine you have a piece of wood where this is the direction of the fibers. And then you apply a stress in this direction where your stress matrix is diagonal. 1, 0, 0, 0, 0, 0, 0, 0, 0. Is epsilon diagonal? Not necessarily, because you will find shear strain because of the orientation of the fibers. You will get some shear strain. So you might get epsilon that's equal to a value here and a value here and a value here, and values here, and maybe a value here as well. Not necessarily diagonal, because this material is orthotropic. In this case, I intentionally apply the stress not in the direction of the fibers, because if I apply the stress in the direction of the fibers, I might end up with a diagonal strain matrix. If this is a linear elastic isotropic material, then you will find that both principal stresses align. Sorry, both principal directions of the stress matrix and the strain matrix align. Now, in one of our assignments, probably the next assignment or the one after, we're going to investigate this, what we call this, when you're doing it at the small deformation, and when you're using a small deformation analysis, what happens if I actually rotate a material? So in general, I'm expecting that if I have this object, and then I take the four corners and put them somewhere else such that they keep their distance, and all I did was just translate and rotate the object, I expect that the strain should be equal to 0. I don't need any internal stress to change this object. Because I don't need any internal stress to move this object from this position to this position, I should expect that my stream measure should give me 0. However, the stream measure that we're using, and that everybody in any small deformation analysis, has a limitation that if this rotation is high, if this is a very high rotation, then you will find that when you do the analysis, you'll find that the inside the material it's going to start developing stresses. The reason why it's developing strains, simply because you're rotating, because the measure that you're using predicts strain even though it shouldn't. How does it do this? And you're going to have to do this by hand at some point in one of the future assignments. If this is the old position, the new position is equal to a rotation matrix multiplied by the old position. And we understand what a rotation matrix is. This is a vector. This is a vector. And Q is an orthogonal matrix. Then the displacement, which we need to calculate the strain, is equal to the old position, to the new position minus the old position. X is a vector minus another vector. This vector is equal to a matrix multiplied by a vector minus the vector. In order to do this, it's almost like saying Qx, or it is like saying Qx minus the identity matrix multiplied by x, which allows me to take Q minus I multiplied by x. So my displacement is equal to Q minus I multiplied by x. In order to calculate the strain, I have to calculate the gradient of U. The gradient of U is basically how much U changes with respect to x. It's a linear function. U is a linear function of x, and this is equal to Q minus I. So the matrix gradient of U is equal to the matrix that's multiplied by x. And so the strain matrix is equal to half Q minus I plus Q transpose minus I. So if Q is, or if theta is very small, for example, Q is equal to cosine theta, sine theta, sine negative sine theta, cosine theta, 0, 0, 1, 0, 0. What will happen when theta is very small? This is almost equal to 1. Cosine theta is almost equal to, and sine theta is almost equal to 0. And this is almost equal to 1, almost equal to 0. So you'll find if theta is very small, epsilon small is equal to 0. So this matrix that I'm using will give you, is adequate when the object is not rotating. But once the object starts rotating, it will predict strains even though there is no strain, because the material is not really moving with respect to each other. And in solid mechanics, we're going to introduce other strain matrices that would not have this problem. All right, so we'll give you 5 minutes, and we'll jump to the